Hooke's law is what we want to look at first. This is when the restoring force on an object is proportional to its displacement. What this really means, if we look at this picture, is that if we say have a mass on a spring and it's bouncing back and forth like this, 0 right here is its equilibrium position, and the further it gets away from that equilibrium position, the harder it's being pulled back towards the equilibrium. So that force is greater the further away that gets, and it's always, because it's a restoring force, pulling it back towards the center from wherever it's at. Mathematically, Hooke's law looks something like this. You could say our elastic force is equal to negative kx. Okay, so here we have the force, that restoring force, the negative, indicating that it's always moving it back against its motion, always working against its motion to bring it back. And then proportional to displacement, so that's the x. X would be distance it's from equilibrium. And k is what we're used to from energy with our spring constant, right? So it'd be the spring constant of the spring, or there's other applications for that spring constant as well. But it's always sort of the constant, like how hard is the material going to pull back, right? How strong is the spring, or whatever it is you're using. Two definitions we wanted to know about. Period is the time to complete one cycle of motion. So the time to, say, start from one end of the motion, go to the other end, and come back. Frequency is the number of cycles per second. So how many of those back and forth cycles in 1 second would this motion complete? Equation-wise, for period, we use a capital T for time, a time, but a very specific time, how much time it takes to complete one cycle, and F for frequency. Now these two things are inversely related, right? You can see they both sort of depend on time and how many cycles. So they're exactly inversely proportional of each other in that period equals 1 over frequency, or you could say the frequency equals 1 over period. This brings us to our kind of big category of motion that's simple harmonic motion, or SHM. This is a system of motion, maybe we could say, whose net force is described by Hooke's law. So essentially it's anything that obeys Hooke's law. So if we come back to our mass spring system, which is a good example of simple harmonic motion, we can kind of add a couple things to our picture now. Here, this point where we're at 0, we would call this our equilibrium. So that's sort of the point about which the motion is happening. It's sort of our starting location. It's the center of this bouncing back and forth. The other important thing we want to know here is that this distance here, and also true for this distance here, is what we would call our amplitude. And our amplitude is our max displacement from equilibrium, right? It's the furthest away that we get. Now for simple harmonic motion, right, we talked about period and frequency and what those are. The reason we talked about those is because that's one characteristic of simple harmonic motion. Right? Simple harmonic motion has a certain period to it, a certain time it takes to complete that back and forth, and it also has a certain number of cycles it completes every second, so it has a frequency. So the equations for that, for kind of any, especially a mass spring system, would be 2 pi square root of m over k. And that'll help calculate the period of that motion. So 2 pi square root of mass over our spring constant. And since frequency is the inverse of period, we could write frequency as 1 over 2 pi square root k over m. So just kind of flipping everything around there to get frequency. So we want to calculate the frequency of a car's oscillation when it has bad shock absorbers. So when the shock absorbers aren't working, they're not what we call damping the motion of the suspension in the car. It's just going to let the car bounce up and down. And so the car has a mass of 900 kilograms, and we have our spring constant of 6.53 times 10 to the 4th newtons per meter. We want to know frequency. So frequency is 1 over 2 pi square root k over m. So the frequency of this motion is going to be 1 over 2 pi square root of 6.53 times 10 to the 4th newtons per meter. And then our mass is 900 kilograms. One important note here before you go and punch this into your calculator, it's very important that we pay attention to how we use parentheses here. Probably the most common mistake I see is that when you're doing this 1 over 2 pi, you have to put parentheses around it in your calculator like that. It's a very easy thing to forget to do, and you will not get the right answer doing it. So you have to put, if you forget to do it, so you have to put parentheses around that. So if we plug all that into our calculator correctly, we should get 1.36 hertz for our frequency. If we wanted to find the period of motion, remember that period is 1 over frequency, so we could pretty easily find that and just do 1 divided by our answer there, 1.36, and find a period of motion of 0.74 seconds. And even though it didn't ask for it, very quick to solve for period there.